Hey y'all, today we're going to be looking at a specific type of function called a linear function. So last time we went through the process of going over what is a function and what isn't a function. We also discussed the domain and range of a function. And so today we're going to actually look at one specific type of function called a linear function. And so simply put, a linear function is just any function that has a constant rate of change. So our overarching question for today is going to be what type of relationship has a graph that is a line. So spoiler alert, it's a linear function. But we're gonna get into what that means to have a constant rate of change and that sort of thing. So in order to determine whether or not a function is linear, we have to determine whether or not the rate of change is in fact constant. So I'm using this word rate of change. You may have heard it described as being the slope of a graph in 8th grade. So the first thing we want to do is determine what is the rate of change. And specifically, is it constant? Okay, so we want to analyze that rate of change to determine if a function is linear. And it will be linear if the rate of change is constant, meaning that it doesn't change. It has some very specific value. So not only do we want to look at the rate of change, but in order to write these functions, these linear functions, we're also going to need to know the initial value, or what I'll later call the y-intercept. You may remember from 8th grade dealing with this little equation right here, y equals mx plus b. That is going to be the format that we're going to use to write linear functions. Okay, so if you've seen an equation like this, like let's say like y equals 2x plus 10, that would be an example of a linear function. So let's go through some vocabulary terms here. Some of these are from last time, like independent and dependent variable. So for instance, I like to start with the independent variable because that is your input. Maybe I'll say input or your x values. The independent variable is going to be the variable in a function that represents the input values. So we'll say that definition is D. The dependent, on the other hand, that is going to consist of your output values. Usually they're going to be the y values. So the dependent variable is going to be the variable in a function that represents the output values. If you're looking at a coordinate, this x comma y coordinate, the first number is your independent value and the second number is your output or your dependent value. The initial value, we're going to define that as the output of a function when the input is 0. So if you have a coordinate 0 comma something, whatever that something is going to be the initial value. Now typically we're going to use, if you see the equation written as y equals mx plus b, then the initial value is the b value. So I'm actually going to change this question mark to a b. So whatever that number is, that's your initial value. The rate of, I'll do this one last, but the rate of change is the ratio of the dependent value with respect to the change in the independent value. This is going to be the m, the value of the coefficient of x here. Now the way we calculate rate of change, there's a couple of different ways, and I'll get into it a lot more detail in a minute, but basically you want to be thinking of like rise over run. Okay, if you're looking at a graph. If you've got 2 points, you want to look at delta y over delta x. And I know I'm kind of throwing out some Greek letters at you, but basically what the delta means in this context is change. The change in y over the change in x. A little bit more specifically, if you're more of like a formulaic thinker, what this really means is y2 minus y1 over x2 minus x1, where the x1, like these are coordinates. So like let's say you're given 2 coordinates like 2 comma 3 and 5 comma 6, and the question is to find the rate of change between these 2 values. Well, then you just label one of them x1, y1, and the other one x2, y2, and then those are the numbers you'd plug in here. Lastly, the linear function is going to be any function that can be written in the form y equals mx plus b, where m and b are real numbers. Remember, m is the rate of change, and b is the initial value. So let's look at a situation here and see if we can determine the independent and dependent variables. It says Michaela earns $8 per hour at an after-school job for a function that gives the amount earned for working a given amount of hours. So the independent variable, which is our input here, is the number of hours she worked. Okay, so the reason why we say that is because the amount that she's earning depends on how many hours she works. So that phrase depends on is really going to be the clue as far as what's independent and what's dependent, what's input, what's output. Okay, the output is the amount earned. There's two ways that you can sort of describe this. One way is to say that the amount earned depends on the hours worked. Okay, another way, let me move that up a little bit here so my head gets out of the way. Another way to say this is that the amount earned is a function of, go back to that word function, the hours worked. Okay, so either these two phrases basically mean the same thing, but in general, you're going to list your dependent variable first, dependent, and your independent variable last. Because the dependent variable is dependent because it depends on something else. In other words, you're going to determine this based on whatever value this has. So if I say, I worked 5 hours, how much did I earn? Okay, I know up front what my independent value is, and then my dependent value depends on that. So let's look at a scenario, or let's kind of, well, it's the same scenario here, but let's dive into it a little bit further. So if she's earning $8 per hour at her after-school job, if she worked at 0 hours, she's going to earn obviously $0. Okay, if she works for 1 hour, she'll earn 8. 2 hours, 16, and so on. Basically, we're just adding $8 every time we move down in this table. So the domain of this scenario is going to consist of all the positive values and 0. Okay, so an easier way of saying that is all the non-negative values. Okay, another way that you can write that, though, is we can say x is going to be greater than or equal to 0. What's the range of the scenario? Well, also all the non-negative numbers, right? Because we do want to include 0, but we want to include every number that's bigger than that. The way we would write that using an inequality would be y greater than 0. So the domain is x greater than or equal to 0, and the range is y greater than or equal to 0. So now that we've got this table all laid out, let's talk about how you compute the rate of change. Okay, so the way you compute rate of change, and I'm going to use the variable m, like y equals mx plus b, to represent rate of change. Okay, rate of change is my m value, is the change in y divided by the change in x. So what you typically do is, first you want to know, is the rate of change actually constant? And so what you'll do is you'll look at just 2 sets of values at a time, and you'll measure, or you'll compute what the change in y and change of x is. So these values over here, these are my change in y's. These are my change in x's. And so what this is saying is, like, to get from 0 to 8, we've got to add 8. So between this coordinate and this coordinate, my change of y is 8, and between this coordinate and this coordinate, my change in x is plus 1, because going from 0 to 1, you have to add 1. So for this change, I can determine my rate of change is 8 over 1, which just equals 8. And what you'll see is, in this particular case, every single time we're changing, 8 divided by 1, we're going to get the same number every time. So, this change is going to be 8, this change is going to be 8, this change is going to be 8. And because all of these numbers are the same, we can say that we have a linear function. Okay, these are the same, or these are equal, so we have a linear function. When we have a linear function, we can go ahead and compute the rate of change. The rate of change is the ratio of the change of the dependent value with respect to the change of the independent value. And we compute it by dividing the change in the dependent value. So I'm going to write this little delta again, the change in the dependent value divided by the change in the independent value. So that's going to be 8 over 1, which is 8. So my rate of change here is 8. Now we can also graph this and to see what a linear function looks like. So we're still dealing with our good friend Michaela here. It says she earns $8 per hour at an after-school job. The graph shows the relationship between the number of hours Michaela works and the amount that she earns. Okay, so this is just a graphical representation of that same table we've been dealing with. When all of your points are lined up like this in a straight line, you know you have a linear function. Okay, a linear, or I'll say, here I'll do this. The graph of a linear function is always a straight line. Okay, it's always a straight line. So if you ever see a graph that looks like a straight line, boom, you know it's linear. You don't even have to compute anything if that's all it's asking. We can also verify the rate of change here, but we do it a little differently. Remember that the rate of change is the change in y over the change in x. And if we're given a set of tables, we actually want to compute those values. But if we're given a graph, we can use the slope of the line to determine this. Sort of casually, we call this the rise over the run. You always run to the right, and then the rise can either be up or down. If it's up, then you know your slope's going to be positive, but if it's down, it'll be negative. But you always run to the right. So you're going to read this graph like you would read a book, right? A sentence goes from left to right. So from left to right, we can see that to go from here to here, go up 8 over 1. So my rise is 8, and my run is 1. Up 8 over 1, up 8 over 1, and so on. So, we can verify that slope, or that rate of change. A linear function describes the relationship between two quantities having a constant additive rate of change. The graph of a linear function is a straight line. Okay, so that's basically what I was saying earlier. Let's look at a different scenario. Enough of Michaela and her $8 an hour job here. Let's get another one going. Manuel is selling baseball caps at a fundraiser. The table shows the relationship between the number of caps sold and the amount of money he has collected. So our independent variable here, wow, I can't spell, dent, is the number of caps sold, and the dependent variable is the amount of money he collected. And that's all given in this table here. So let's figure out the rate of change. We want to first verify that it's constant, okay? So to verify that it's constant, we need to double check the change in y and the change in x for all of these. Now, it doesn't have to necessarily, like all these change in y's don't have to be the same. That doesn't really matter. But what does matter is when you divide the change in y and the change by x, that ratio is the same. So like here I've got plus 5, here I've got plus 2. So my change in y over change in x is going to be 5 over 2. We don't know it's linear yet, but we'll verify it on the next step. Here we have plus 5, and here we have plus 2. So this one's pretty obvious. My change in y over change of x here is going to be 5 over 2. These are the same, right? These are equal. So we know we have a linear function. So if you check these, and these are not the same, then it's not linear. You do want to be a little careful, though, because let's say instead of this point, I had something like, let's say this point was 25, and 8 comma 25. So if you, let's check the rate of change there. So here I'd have plus 10, and here I've had plus 4. Now, if you're just working through this very quickly, you might jump to the conclusion that, oh, it's not linear because the, plus 10 is different than plus 5. But if I actually calculate the rate of change here, I would have 10 over 4, which actually reduces to 5/2. So it is, in fact, equal. So you don't have to, these don't have to necessarily be increasing by the same amount. As long as the ratio is the same, then you're good to go, okay? So that's a little minor point, but that will definitely come up from time to time. The rate of change here is the dependent change over the independent change. So I'm going to just throw this delta in there just to emphasize that. But we've already computed this. This is 5 over 2, which is 2.5, or $2.50 per cap. So now we know how much each individual cap costs. There is a constant rate of change, so the points will make a straight line or a linear function. So let's try to graph this out. Let's see what the graph of this thing looks like. We can verify that it's linear by checking that graph and making sure that all the points lie along a straight line. Now the initial value is going to be the start value. We don't exactly know what that is yet, although it won't be too hard to figure that out, especially because these numbers are pretty small. But let's go through this real quick. This is the same situation, and those 3 points that were on the table before are listed here. This graph is discrete, meaning that the graph is just made up of individual points. We don't really want to draw a line through this because you can't sell like a half of a cap, right? Like, have you ever gone into a store and say, oh, I want half a hat? Yeah, that doesn't make sense, right? So we really want to just keep the points that are valid here. So there are some other points that aren't on here. We just don't want to connect the line and indicate that we want to include every single point. We just want to include the points that would be feasible for this context. So like if we know that these caps cost $2.50, we can estimate where some of these points should go. Like 10 plus 250 would be like roughly here. This one's what is this? $15 plus 250 would be $17.50. And we could work backwards, right? 10 minus 2.5 would be 7.5, and 7.5 minus 2.5 would be 5. So let me label this a little bit. This is 5. This is 7.5. This one's 10. That's pretty obvious. This one's 12.5. Oh, you know what I'll do? Yeah, maybe I should write these as coordinates to make it a little clearer. So this point is 0, 5. This one is 0, 7.5. This is the, not 0, oops, oh boy, 1, 7.5. This would be 2, 10. That one was the given point. This one would be 3, 12.50. This was the next given point, 4, 15. This is one that we inferred, 5, 17.5. And then finally, we have 6, 20. So the domain here is going to be all the whole numbers. Okay, so all the whole numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. Manual started this fundraiser with $5. We can see when x is 0, y is 5. The range is going to be all these values that are greater than or equal to 5. They start at 5 and go up from there. So if we wanted to write an equation to represent this, we could. It won't be that bad. Y equals mx plus b. The slope here we already determined before was 250. So it would be y equals 250x plus the start value, which was 5. So this would be the equation that would model this data. So let's, we've talked a lot about rate of change, and we know now that a linear function or a function is linear when the rate of change is constant. So let's try to determine, if I give you some information, you tell me if it's a linear function or not. A linear function has a constant additive rate of change. Okay, meaning you're adding or subtracting the same amount every time. A nonlinear function doesn't. So let's look at this table and see if we can determine what is linear and what's not. So we've got 3 different things here. We've got time, height, and distance. Really, this is going to be, you're going to think of this as like two different tables. Okay, like here's x, and I'll call this y1 as like the first table. And then you've got x, and then this other one, y2. And really what we want to know is which table's linear and which one's not. Time versus height or time versus distance. So if you look at the time, you can see that it's increasing by 1 every time. If you look at, this is gonna work out nicely. If we look at the height, this increases by different amounts each time. 5.3, 2.7, 1.8. If you look at the distance, this is increasing by the same amount every time. So computing the rate of change, here I would get 5.3 over 1. Here I get 2.7 over 1. So clearly that is not linear because we're getting a different rate of change for each change. So a nonlinear function means it does not have a constant rate of change. On the other hand, the distance is changing by the same amount, right? We got 17 divided by 1, 17 divided by 1, 17 divided by 1. All of those are going to be 17. And since that is constant, we do in fact have a linear relationship between time and distance. So distance versus time is a linear relationship. Height versus time is not in this problem. So let's look at, see if we got something like this. Is this linear or not? I don't even have to like look at any of the values or anything. This is a straight line. I mean, you might want to double check just to make sure they're not trying to trick you or something, but like if we got a weird scaling going on. But yeah, this is a line, so we could say right away, yeah, this is going to be a linear function, okay, and because it makes a straight line. If you wanted to compute the rate of change, you would do the rise over run. In this case, our rise would be, let's see, okay, so this is going by 5, so we want to be careful here. This is like 5, 10, 15, 20. So I'm going up, what is that? What point is this? So this point is 1, comma 5.3, and this point is 1, oh, no, I'm sorry, 1, comma 17. This is, we're talking about distance here. 1, comma 17. And this one is 2, comma 34. So my change in y, my rise, is going to be 17. My change in x from 1 to 2 is just plus 1. So that would be my rate of change. This is a graph that's showing the relationship between time and height. We know right, just looking at the graph without computing anything, we can tell real quick that this is not a function, a linear function. It is still a function. It's just not a linear function because it doesn't make a straight line. It's pretty straightforward here. If you check the slopes here or the rate of change from here to here is going to be different than the rate of change from here to here, and then especially over here because you're negative over here. One thing that I don't think I've really pointed out here, I know I've been emphasizing that a linear function makes a straight line, but just look at the word linear. It's got the word line right in there. In fact, that's why it's called a linear function. So you can hopefully make that association pretty easily. Let's look at one other thing here. So this says, compare the different linear representation of Rex and Max's growth as puppies. Which puppy grew at the faster rate? So what we're going to do is we are going to compare rates of change and see which one's growing faster. So let's look at Rex. Rex's rate of change, let's make sure it's linear. Okay, so this is plus 2.5 and this is plus 1. Okay, so the first rate of change is 2.5, and then the second rate of change, it looks like it is going to be linear here. I kind of assume that it was just because of the context of the problem, but it's good to double check here. So the rate of change here is 2.5 over 1, which is equals 2.5. And then Max's rate of change, let's check this out. Now they're given these points, luckily they give us the coordinates here because otherwise we wouldn't really know what these are. Okay, this change in y from 5.7 to 8.2 is 2.5. The change from 0 to 1 is 1. So actually it looks like they're growing at exactly the same rate, 2.5 pounds per week. Both puppies have a rate of change of 2.5 pounds per week, so neither grew at a faster rate. They're growing at the same rate. Rex weighed some number of pounds at birth. Max weighed some number of pounds at birth. Okay, so Max's is a little bit easier because you can see it right here. It's 5.7. But how big was Rex? Now, right now, I think the easiest way to do this is just going to be to work backwards in the table. So I'm going to just like continue the table over here, 211, and then 1 something, 0 something. And so this is going to be where our answer is. But if I'm adding 2.5 pounds every week, I can subtract 2.5 pounds, working backwards to try to figure out what that is. So 11 minus 2.5 is going to be 8.5. And 8.5 minus 2.5, again, is going to be 6. So Rex weighed 6 pounds at birth. And so if the question is like who weighed the most at the time of birth, we'll say Rex did. And we can actually write equations for both of these growth rates. If we want to write an equation for Rex, we would say, okay, his rate of change was 2.5 and his initial value was 6. So that would be the equation to represent Rex's growth. And then if we want to write an equation to represent Max's growth, we would say y equals 2.5x plus 5.7. He had the same rate of change, but a different start value. All right, so what type of relationship has a graph that is a line? Okay, so this is just kind of summarizing what we talked about. So the answer here is if a function has a constant rate of change the function is linear. This is really the key takeaway for today, is if you've got that constant rate of change, you know that the function is going to be linear. All right, and just to recap some of these other terms, the rate of change is the ratio of the rate of change in the dependent quantity with respect to the change of the independent quantity. A linear function describes the relationship between two quantities having a constant additive rate of change. We're getting a little redundant here. I'm not really saying anything I didn't say before, but we're just kind of summarizing what we learned. The graph of a linear function is a line. Specifically, it's a little redundant to say straight line, but I think it gets the point across a little better. A straight line. Okay? The initial value is going to be the value of y when x is 0. So in this case, it'd be like 5.75. And then the rate of change would be this plus 1.5 over plus 1, which would just be 1.5. So hopefully this is making sense to you. Again, the key takeaway here is that a linear function has a constant rate of change. And we looked at how to find that rate of change, whether on a graph we can use rise over run, or using a table of values, we can just compute it like this. Y'all have a great day, and I'll see you around.